Okay, so we're going to look at the optimization problem. What is an optimization problem? It is the process of making something the best it can possibly be given certain constraints. It involves maximizing or minimizing a certain value or quantity. How do we recognize that we have an optimization problem? Because the words absolute extrema are very rarely used in an applied problem, application problem. We want to look for some clue words that might indicate that we're going to be doing this. Your obvious: maximize, minimize, most, greatest, fastest, farthest, smallest, cheapest, closest, things that reference in that fashion. Okay. Optimization problems are just absolute extreme problems in disguise. Okay, so we've already talked about that, and so we already know what we're going to end up doing. So let's take a look at this, and so let's see, how do I solve one of these things? What is the process I want to follow? You want to write an equation for the quantity that you want to maximize or minimize. Okay, this equation that you want to maximize or minimize is what I refer to as the primary equation. Okay, the primary equation, the one you're going to maximize or minimize. You're going to use the constraints to find relationships between the variables, if need be. Our goal is to get the first primary equation with only one variable in it. So I might need a secondary equation to help me find a relationship between certain variables using the constraints. Once I have that, we want to rewrite the primary equation in terms of only one variable. And then we're going to take its derivative and then find the critical values and then use the candidates test to find the extrema. Remember, the candidates tests are all the relative extrema and the endpoints, if we have any. And then we want to make sure that we interpret our answer in context to the problem. We want to make sure that we answer the question that was actually given. So let's go ahead and do some examples of these. I have a couple of them, about 4 examples we're going to walk through, showing you different looks. Okay, so here we go. Here's the first example right here. You want to enclose a garden with fencing to keep the rabbits away. A shed will serve as the boundary for one side of the garden, and fencing is needed for the other 3 sides. If you have 60 feet of fencing, what is the area of the largest garden you can enclose? Okay, so as we look through this, we can see clearly that we want to enclose the largest garden in its area. We're going to make a 4-sided fencing, so a rectangular shape. And so the process we want to follow for this thing here is we want to draw a picture of our garden. So I have the 3 sides and then the shed, which I'll draw this way. So this is the shed. This is a rectangle, so I have a length and I have a width and a width. And the lettering doesn't really matter. This is just how I labeled it. I like to write down the word that's going to represent our primary equation, so the area of this rectangle. So the area is length times width. Okay? So we can see that we have 2 variables over here, so we're going to need to find a secondary equation that can relate these variables so that I can get one variable in this equation over here. So what could I possibly use? Well, they said I have 60 feet of fencing. So that means the fencing to go around it, that is a perimeter, and that is my secondary equation. So the perimeter is 2, sorry, in this case there's only 1. So in this case I have 1 length and 2 W's, and I know that has to be 60 feet of fencing. So from this right here, I can then solve for one of the variables. Obviously, L is the easiest one to solve for, minus 2W. And so this becomes our relationship between the variables, and I can take that quantity right there and plug it into that equation over here and get the area formula with only 1 variable in it. So this is my primary equation with 1 variable, so now I can go through and find its derivative. So what is the derivative of the area with respect to W? If I distribute this and all that kind of stuff, I'm going to get dA dW is going to be 60 minus 4W. Okay? So then I want to do what? Well, now I need to find out where this thing is equal to 0 or undefined. It's a polynomial, so it's defined everywhere. So when is 60 minus 4W equal to 0? Well, when W is equal to 15. And that would be my critical point. Okay? So, candidates test. Here's my W. What is my A for this W? Well, the smallest value of W I can possibly have would be 0. And the largest possible value I could have, since I have 60 feet of fencing, is each of these W's could be 30, meaning there's no length at all. But these could be 30. The area, if W is 0, is 0. And the area, when W is 30, is also 0. And so 15 is really the only point that really is going to serve any purpose. And so that I can figure out what this is. What is the area when W is 15? Well, I have to come over here and find this length, 2 times 15, and we get W is going to be 30. And so then the area is going to be 15 times 30, or 450. So this is 450. Okay, so what can I conclude from this? I conclude that I can get the largest area of 450 square feet when W is 15 and L is 30. So the largest enclosed area is 450 square feet when W equals 15 feet and L equals 30 feet. So that's my answer in context. Okay? So let me go ahead and show you all the little side notes that I had for this problem, then we'll do the next one. So kind of laying out how I went through this problem over here. This is pretty much the same. Solving optimization problems is just like finding the absolute extrema, but you often must create your own equation to maximize or minimize. And that's what we had to do here. We had to go through and find this primary equation based off of the story that we had. Okay, let's take a look at another one. You can pause here and copy all that down if you need. All right, so let's take a look at another one real quick. We want to construct a box whose base is a square and has a volume of 36 cubic feet. The material used to build the top and the bottom costs $8 per square foot, and the material used to build the sides costs $6 per square foot. Determine the dimensions that will minimize the cost of building the box. Okay, so just like before, the first thing I want to do is I always, if I have a geometric shape, is I always draw the geometric shape as best I can, labeling what I know. Again, you just do the best that you can. You're just trying to represent what you're doing. So here is a box. The base is a square, so they both have the same value here and here. And then it has a height. Okay? And the volume of this box, because I have a box, we talked about the volume being 36 cubic feet. In this particular example, is going to be x times h. And I know that's 36. Okay? So what do I want? This is not what I'm minimizing or maximizing. I'm minimizing the cost, so this becomes my secondary equation. So what is the cost of this? Well, the cost, which I'll use here, is $8 per square foot for the top and the bottom. The top and the bottom is a square. I have 2 of those. It's $8. And then how many square feet is this going to be? X times x times 2. 2x squares. The cost of the sides is $6. And what is the area of all the sides? Well, all the sides are going to be x times h. And I have 4 of those. So I have 4 xh's. So my cost equation, which I'm going to abbreviate now as, oh, we got to get one variable over here. So you see I have 2 variables in here. I want to get 1. So I'm going to use this equation right here to solve for one of these variables. And the easiest one to solve for would be h. So h is going to be 36 over x squared. And so that's the quantity I'm going to plug in over here and then simplify this out. So my cost equation is going to be 16x squared, 24x times 36 over x squared. And then this will simplify even more to 864 divided by x. So that is my primary equation right here that I'm going to minimize. Okay, so to do that, I need to take its derivative. So c prime of x is going to be 32x minus, and then this is going to be 864 over x squared. And I need to know when this is going to be equal to 0. And you can use a calculator to help you solve all this out. I did already. I ended up getting x equals 3. Okay? So if x equals 3, I can come over here and find h. 36 over 3 squared, and that will be 4. And then I want to do my candidates test because I have the x and then the cost. Okay? Obviously, if x is 0, then I don't have a box over here. The cost would be undefined. We don't know what that is. Okay? I got to do 3. And then what's the largest I can have? Okay? Well, the largest I can have here to have a volume of 36 is if x is all of it. Okay? And so then you end up with that right there as 6. Okay? And then what you end up with here is working this out, plugging these numbers in. You can get the cost to be 432, and this one over here is to be 720. So from that information right there, and you can take all the numbers and do all the extra work for all these things. Doing all this right here, you can see that the minimum cost is going to happen right here. Okay? And so that's how we answer our question. Let's go ahead and answer this question out then. The cost is minimized when the dimensions of the box are 3 feet by 3 feet by 4 feet. And then with a minimized cost of $432. Okay? All right, so let's take a look at another example right here. Here's an equation, x squared plus 3x minus 5 represents a parabola. Name the point on the parabola that is closest to the origin. Okay? So we got a parabola here. We want to find out when it's closest to the origin. All right? And so what does that even mean? Well, we can take a look at this thing and we can graph this out very quickly, or sketch it out even better. Okay? We need to know basically where it's at. I know when x is 0, I'm at -5. Okay? And so we can go and find some other ones over here and figure this thing out. But basically what I have is I have a vertex, and it's going to come across this way, and it's going to come across this way. And what I have is I have some generic point. I'll just use this point right here. Here's some point called x and y, right? And I want to know when the distance to the origin is the smallest. Okay? I want to be closest to the origin. Where is that going to happen on this entire parabola? So this is just a representative point. Okay? And so what I need to do is I need to find my primary equation. the one I want to do. So that means I have to find a distance. This is why I draw this picture. So I need to find out when that distance right there is the smallest. So how do I find the distance here? How do I make an equation for that? Well, just keep in mind that this is just a Pythagorean theorem thing. This is the y value, this is the x value. So this distance is equal to the square root of x squared plus y squared. That is your primary. But I have two variables, so I need to be able to get one variable in here. Luckily for us, they told us what y was, sitting right there. Okay? And so we go and plug that number in, and we get our distance is equal to the square root of x squared plus, and then this quantity right here, squared. Now, we are going to use the calculator for this kind of stuff, okay? And so we're not going to spend a lot of time going through this thing and doing this, trying to do this by hand. It'd just be too difficult at this point. But using your calculator and stuff, and to determine when is d prime of x equal to 0, when is that going to happen? Then we get some values here, and we'll get it when x equals a negative 4.011, when x equals a negative 1.611, and when x equals 1.152. Okay? And then we can use our candidates test, and we can test these points out. Okay? And I have a negative 4.011, and we have 1.152. Okay? And the only reason I don't have this one in there is because if you do the derivative and stuff like that, and you check it all out with the number line, you're going to find out that I only need to look for relative minimums, and there's two of them, and these two are relative minimums. So these are the 3 points, negative 4.011, negative 1.611, and 1.152. This is a relative minimum, so it must have been negative here, and then positive here, and then negative here, and then positive here. And so you can see that we have two minimums, and that's why we're looking at those. There are no endpoints in this problem because the problem is going on forever. And so in using this and plugging these numbers into the original function up here, you're going to get 4.118, and this one will be 1.172. Again, I'm giving you the numbers, but I want you to go through and try and work this out on your own. Okay, so you can see how this is done. And so where is the minimum number? Well, the minimum is right there. Okay. So this is the x coordinate for the minimum. We still need to find the y coordinate for the minimum. Okay. And so we need to take this number right here and plug it up into this thing, our original equation, solving for y. And again, you can use the calculator to assist you in all this kind of stuff. 1.172 equals the square root of 1.152 squared, y squared, and then that gives us a y value that is a negative 0.217. Okay, so the ordered pair the point 1.152 negative 0.217 is the closest point to the origin. Okay, and then there you go. So let me go ahead and show you some of the other stuff that I wrote so you can see that. You can write that down and copy it and all that kind of stuff. Pause right here and go ahead and take a look and write all that down. Okay, so again, work that out. Get good at your calculator. Okay, try and work that out on your calculator, and you might actually need to go and find the derivative by hand and then use that to help you out. Okay, just multiply all this all out and combine like terms, and then you can do it that way. Okay, it'll be ugly, but you can still do it. Let's take a look at the next one, the last one here. Okay, we got an oil problem. The oil is leaking. Oil is leaking from a pipeline onto the surface of a lake, and it forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. Then a recovery device arrives on the scene and begins removing the oil. The rate at which the oil is removed is R of T equals 400 times the square root of T in cubic centimeters per minute. T is measured in time in minutes since the device began. Find the time when the oil slick reaches its maximum volume. Justify your answer. But what are some observations we can look here? So you look at a problem for the first time. What am I looking at? Okay. The volume of the oil slick is a function that depends on time. So we have a V of T. The maximum of V of T is, we need to find the time when the rate of change of the volume is 0 and is changing from positive to negative, and consider the endpoints. And then V prime of T is given as a rate in of 2,000 cubic centimeters per minute and a rate out of R of T. So we got oil coming in at 2,000 cubic centimeters per minute and a rate out right there. So then that tells me that I know that V prime of T is the rate in 2,000 minus the rate out. I need that to be 0. So we plug our numbers into this thing and work this out. This is the 400 square root of T. So I got 400 square root of T equals 2,000. So the square root of T is equal to 5. And so T must be equal to 25. We got a little number line here. 0 is the lowest it can be. Here's the 25, V of T. And then what do I know about my signs in here? Well, this is where it's equilibrium right here. So I have what? Before then, it would be plus, and then after that, the volume of the oil slick will be less. Okay? So I have a relative maximum at 25. So let's talk about what's going on here. Since I don't really have an equation I can use, all that kind of stuff, I have to reason out my knowledge of what's going on. So what this is basically telling me is the pipe started leaking, okay, and it's increasing at a rate of 2,000 cubic centimeters. So that means at 0, I have not reached my maximum volume yet. Okay, and then it reaches up here. This is a relative max. And then what happens? Then the machine is taking the oil away faster than it's being generated. So now I am decreasing. Okay, the volume is decreasing. So that means, and will continue to do so until it's gone. So that means at 25, that is your maximum volume of the oil slick. Okay, so you have to reason that out, and you have to write that out using the context of the information given. So let me just go ahead and show you that, how to write it out, so you can see it. So over here in my discussion, I say, okay, V prime of T is greater than 0 when T is between 0 and 25 because R of T is less than 2,000. And then the other one is greater than that. So that means I have a relative maximum at 25. Okay? You have to establish that you have a relative max here, and you cannot say it by this picture. So you have to tell them why you know that's what it is. For the endpoints, because this is an absolute, you got to consider the endpoints. For 0 to 25, the volume is increasing because the velocity, the volume, the derivative of the volume is positive. So at T0, we have not reached the maximum volume yet. When T is greater than 25, the rate of removal is always greater than the rate of the oil leak. So the volume of the oil slick is continuing to decrease as this time passes. Conclusion, the oil slick reaches the maximum volume at T equals 25 minutes because V prime of T changes sign from positive to negative there. And that's how you want to answer and address this question. So go ahead and pause and finish copying that down. This is the last example. So make sure you ask me questions in class. And that concludes.